In this particular video, we're going to discuss some programming issues, the presence of errors in programming, the use of comments, and the use of subprograms in what is called structured programming. For that, we're going to start looking at our worksheet. There are many types of programming errors, even big mistakes, big screw-ups that you're going to do in your programming, but we could classify them into the following. Syntax errors. These are errors of the programming language. These are figures, actually. They're not real programs. Oh, well, actually, they're real programs. The figures are right here. Anyway, I create this program where I initialize a sum and index, and then I provide an index here that is not even one of the indices that I'm using. So that's going to be a logical error later on. But what I'm missing here is an output for my result. I don't have an S listed like I do here or here. And so that means that even if it tries to calculate this thing, it's not going to give me any result. And so when you try to run it, you get this result that says output value must be defined for the call procedure. That's a syntax kind of error, in the sense that we are not fulfilling all the conditions for the language to work. There is also runoff errors, and these are the ones that show up at the moment you're running your program. You have checked that the syntax is fine, you think the logical part of the algorithm is correct. You run your program and you get this, like, division by 0. Why am I dividing by 0? Because I initialized the value, the index k as 0 first, and I did not increase it before going through this. So k is equal to 0, and n is any value, like it's got to be like at least 2. So k is less than n. But when I try to divide 1 over k with k equals 0, I get a division by 0. That's a runoff error that you got to go into your program and see where is it occurring and what you need to do to fix it. And then you have logical errors, which basically means the program appears to be translated properly, but there is something that's missing, and you got to look into the algorithm and the translation of the algorithm. And this step is called debugging, finding what are the bugs that are populating your program. In this case, I'm actually doing a summation, but I'm getting a value of 0. Why am I getting a value of 0? Because there's something wrong with the control, and the control is this k greater than n. Now, k is never greater than n, and so this is not going to be executed, and the value as they're going to be reported is this one. So actually changing this to less than will fix the problem. And so those are some of the errors that you got to be aware of: syntax, runoff, and logical. Comments. Comments are simply statements that you add into your code to identify parts of the code. This example here is the case of the Frobenius norm of a matrix that we presented in an earlier video, but I have no idea what's going on here, okay? If I wanted to make it more clear for anybody that's going to be using the program, then I will go like click here, enter a comma, and then enter a double quote, and say finding the rows and columns of matrix A, And then if I wanted to indicate something, then we're going to go to the right here and say comma, and double quote and say initialize as in I, and so on. I did the changes in here, and I'm going to remove them from here, deleting. And so that's the idea behind comments, just showing somebody who's going to read the code later what are you trying to do in some steps of the program. Try not to overdo it, and you could put a comment for every line, but that would be overdoing it. And just give key information at key points of the program. And that is the use of comments in Math Studio programs. Subprograms. To illustrate the idea of subprograms, I'm going to use a problem related to open channel flow. I was a professor of civil engineering for many years, teaching hydraulic engineering. In this case, we have a trapezoidal cross-section characterized by a bottom width P, side slope Z, that means how many horizontal units every time that you climb a vertical unit, and a flow depth Y. If you look at the longitudinal picture, you get a bed slope. That would be how much the channel bed drops for every horizontal distance along in the X direction. The cover of the channel bed is characterized by a number called the Manning's coefficient N. That's the depth of flow again, and we're trying to calculate velocity and discharge. For a trapezoidal cross-section, it turns out that the area is given by this formula. The weather perimeter, which will be the length of the boundary of the channel that's in contact with water, that would be AB plus BC plus CD, is given by this formula. The top width is the distance AD, which is the width of the water surface. It's given by this formula. And for the calculations, we use the hydraulic radius, which is the area divided by the perimeter, and the hydraulic depth, which is the area divided by the top width. The velocity is calculated using something called the Manning's equation, or the Manning's formula, where we have a constant Cu that depends on units. Is equal to 1 for the SI, the international system, 1.46 for the English system. The Manning's coefficient, the hydraulic radius that we calculated up here, and the slope of the channel bed, which is an input data. Once we have the velocity, we can calculate the discharge. This is the cubic meters per second or cubic feet per second as the velocity multiplied by the area. And then way to classify the flow is to calculate this dimensionless number called the Froude number, which is equal to V, the square root of gravity, multiplied by the hydraulic depth. And so I'm going to overkill here and create my own programs to calculate the area, weather perimeter, and top width. These are simple functions, but they can be treated as subprograms. Also, I'm going to create some subprograms to select the value of the gravity. Select G, 9.86 if we use SI, or 32.2 if we use the English system. Select the coefficient Cu. Remember that coefficient that's presented in here. And that would be equal to 1 if we use the SI, or 1.486 if we use the English system. And then in here, actually, I don't need these things. Because I'm calculating them in separate subprograms. So my subprogram select U, and then select the units, is reduced, and it depends on whether you use SI. You're going to have meter square, meter, feet per sec. Sorry, I made a mistake here. This should not be feet per second. This should be cubic meters per second. No, meters per second. Sorry, this is velocity, and the discharge should be cubic meters per second. For the international system, the last empty space here is for the Froude number, which is dimensionless. And for the English system, where we use feet per second and cubic feet per second. So here's the program. I provide B, the bottom width, the flow depth, the side slope, the channel bed, Manning's coefficient, and the system of units as a string, whether SI or ES. And then I proceed to calculate. Now I'm using subprograms here. I'm calling that subprogram, which in this case is very simple, but it could be more complicated. So you could justify that. Weather perimeter and top width. So these three calls here use subprograms. Then we calculate this within the program, this within the program. Then I'm going to calculate my G by using a subprogram. Select G, CU by the select CU program, and VU. This is the velocity unit, or vector units actually. Select the units for the system of units, and then you can proceed to calculate the velocity, the discharge, the Froude number. Create a vector. By the way, when I select these things, I use the transpose because it's going to be like a column vector. Same in here. The VQ is the variables whose value are going to be listed as a vector. And then this is simply a statement saying A equal, P equal, T equal, and so on. And then I put together VN with VQ and VU, and I got my main program flow calling these subprograms and this subprogram calling six program. But I made it relatively simple so you can understand the idea. This is called it's not structured programs that use as a structure. This is called it's called modular programming. You divide your program in modules, and then you bring them together in a main program. Okay, and so if I call, remember this is B, this is the side slope, this is the depth of flow, this is the bed slope, and this is the Manning's coefficient, and this is the unit system. In that case, I obtain these results: my area, perimeter, top width, hydraulic radius, hydraulic depth, velocity, discharge, and fluid number. Or if I go for the English system with other values for the input parameters, then I'm getting this particular result. And that's the idea behind this modular programming. And with that, we're going to conclude this particular video.